Okay, it's a pleasure to restart this series of seminars. It's been almost 1 year since the last one, but don't worry, we will be more present this year. And our first seminar of the year is by Juliette Monsel from Chalmers University, and she will talk about energetic cost of work extraction, information erasure. And Juliette, let me know if you like. What we do typically is to let the discussion at the end of the talk, but I mean, it's your style, your choice. You can let people ask you questions during the talk or as you prefer. Maybe I would recommend letting people you talk and then keep the questions for longer discussion at the end. Right?
Yes.
So the stage is yours. Shut up.
Thank you for the introduction, and hello everyone. It's really a pleasure also to be here to restart this Quantum Energy Initiative seminar series. And as was said, I want to talk about energetic cost, first of work extraction, and then on information erasure. Because I have two really different parts, maybe I can take questions in between my two parts. Maybe it's better also because they're quite different. But first, I wanted to just tell you a bit more about what I'm currently doing. So I'm a researcher in Janine Spätzwisser's group at Chalmers University of Technology, which is here in Gothenburg in Sweden on the map. So this is the building where I work and a recent group picture. And the group is called Dynamics and Thermodynamics of Nanoscale Devices. And we are interested in a wide range of topics from optomechanics to quantum transport, with, let's say, special interest in noise, fluctuations, and bounds, and also on non-thermal thermodynamic resources. So what I want to talk about today fits quite well in the thermodynamics of nanoscale devices, as you will see. But first, I just want to go back a bit further and start from, let's say, 19th century thermal machines, just to set a bit the scene. So in this kind of thermal machines, the goal is to perform some useful task. And for that, we are exploiting the cyclic transformation of a working substance, so for instance, steam. And if we're looking at a heat engine, we exploit this working substance to extract heat from the hot bath and convert it into work, and for instance, make this train move forward. We could also want instead to reverse heat flow. So we use work now and we make heat flow from cold to hot, and then we get a refrigerator or heat pump. But in a nutshell, we want to perform some useful task, and it clearly has a cost. And we can use this framework of thermal machines and thermodynamics to quantify this cost. So for instance, for the heat engine, we are consuming the resource here we're using is the heat from the hot bath, or for refrigerator, we are using the work to do the cooling. And this kind of framework is quite powerful, and it's really still insightful. What's really amazing, I think, is that it's still so insightful at the nanoscale. So now we have improved a lot, like fabrication techniques and technologies and so on since the 19th century, and we can really build really small scale thermal machines. And we can still use to a large extent what we understood from this thermal machine framework at that scale. So for instance, this is a heat engine from Lund University, which is generating electric power. So this time it's not cyclic, it's a steady state heat engine. And this other example is an absorption refrigerator based on superconducting circuits from Chalmers, which was published earlier this year. And however, of course, we are at the nanoscale, so we cannot just use 19th century thermodynamics. We have to look at what happens at this scale, and including in particular fluctuations, which can now be as large as the mean values that are considered in classical thermodynamics. We also have to take care of interactions, either within the system or between different parts. And also, if we are looking at quantum systems, then of course we can have quantum effects. So that's a lot of challenges. So for people like me, theoreticians, in the theoretical description, how can we define the thermodynamic quantities and so on, given this new effect at the nanoscale? How can we adapt thermodynamic? But also a lot of challenges on the experimental side as well. So about heat management and also noise to be able to measure and see the effects we want to see. But it's also, from my perspective, very exciting with a lot of new resources as well. So how can we use information, non-equilibrium fluctuation, quantum coherence, entanglement, and so on, to also do some useful tasks, and we can make them fit in this thermodynamic framework. So to give just a few examples related to work I've done. So if we speak about information, you can think about these Maxwell-demon-like devices where you can use information to extract work or do cooling. So I've presented work related to that at the QEI workshop in 2023. You can find the video on the QEI YouTube channel. And I was also there at the workshop in Grenoble earlier this year, talking about this work. And otherwise, we can look at trade-offs and bounds, and we have to change them a bit, because now that there are fluctuations, we can't just look at power and efficiency. It's not enough to characterize the thermal machine, so we have also to look at precision and things like that. And so there are interesting bounds to look into. And on the more like quantum transport side in the group, there are two possible references if you're interested in that kind of topics. And finally, what I'm going to talk about is about the cost of performing some useful operation. And we don't have necessarily to look at really standard thermal machine-like processes. We can also look at, for instance, quantum-mechanical cooling, which is not exactly like refrigeration. And if you're interested, I have also some article about that. But what I want to talk to you about today is more about first quantum coherence and then information. And more precisely, in the first part, I'm going to talk about the energetic cost of work extraction with a qubit coupled to a 1D waveguide and how we can use quantum coherence to help with the work extraction. And in a second part, I will talk of a completely different setup to look at what are the costs involved in information erasure, but more like classical information erasure, with a quantum dot coupled to two terminals. But first, let me start with work extraction. So this is a bit older work that I did during my PhD with Alexia Ophel in Grenoble, and with Marco Fellow-Saziani, that you might know as well from QEI, and Benjamin Huard, who is a researcher in Lyon. And what we wanted to look at is the cost of work extraction. So in the first part, I will motivate a bit and define what I mean by work extraction. Then I'll present you the platform we are going to look into, and finally present the results involving 3 different cases. So if I go back to my introduction, I was talking about these classical thermal machines. So for now, we can think that we are looking just at the work extraction stroke in such a heat engine in classical thermodynamics. And in that setup, the work is quite well defined. It's the change of energy without change of entropy. And this also is typically defined as useful energy. So work is useful energy, and in that kind of like steam engine case, it's typically going to be mechanical energy. And this work that we're extracting from the system, we can either directly use it to set a train in motion, for instance, or we can also store it in a battery for later use. But now the case I'm interested in is not this classical thermodynamic setup, but more quantum thermodynamics. So now my system is a quantum system described by some Hamiltonian HS, and this system is in some state ρS. And this state contains some energy, and I want to extract it without extracting entropy. And let's say the simplest, the straightforward solution for that is to use a unitary operation, because I know for sure that I'm not changing the entropy of the system doing that. So when I do that, that means also that the battery, so this is classical, because it's an external operator which is applying some time-dependent operator, V of t, on my system. So, and in that framework, one more definition which is useful is to know what's the maximum amount of work that I could extract using a unitary, and this is called ergotropy, and of course it's gonna depend on the state ρS of my system. So now to be a bit more concrete and to link it to quantum optics, because this is what I'm going to talk about later, let's look at the example of a maser where I'm looking at a single qubit here, which is excited, and I'm sending some resonant electromagnetic wave on it, and I get stimulated emission, so I get one more photon in my electromagnetic mode. So in that case, my system is the qubit, and my battery would be the resonant electromagnetic mode, and that's both what I'm using to do the transformation, but also where I extract the work, so I've got one more photon. But of course, to do this, I'm using many photons. There are many photons in this electromagnetic mode. So it's clear that this work extraction process has an energetic cost. And what I'm interested in is how much does it cost? And before answering to that and looking into that more, I also would like to know how much work can I extract in the first place from this qubit. And that's where I'm using the definition of the ergotropy from the previous slides, and I can apply it to this system. So I have a qubit, which is in some arbitrary state that are presented here, that I represent here in the Bloch sphere. So it's just a slice in the sigma z, sigma x plane. So my qubit can be represented in this state here, which is characterized by an angle theta compared to my vertical axis. So my vertical axis gives me the ground and the excited state here along sigma z. Then I have this angle theta and then the purity P, which tell me how close am I to the surface of the Bloch sphere, so to a pure state. And for each point here in the Bloch sphere, I can get the ergotropy. And so, for instance, if I'm in the excited state, I will have an ergotropy of h bar omega 0, so here in yellow, because I can do a pi pulse and then bring my qubit in the ground state and extract all of the energy of the qubit. And then on this lower half of the sigma z axis, what I have is all the thermal states, which has zero ergotropy, and I cannot extract any work from them. Well, so what I've been presenting so far is these unitary operations to extract work, and they are quite idealistic. They are not free because we need, in that setting, we need some incoming photons, for instance, to be able to perform them. And we would like to know how much do they cost. But it's difficult in this framework to really quantify the cost because the battery is classical. So it's not part of the model. So what I'm going to present is to consider this time an autonomous scenario where the battery is a quantum battery, which is completely included in the model. So now I have a time-independent Hamiltonian with my battery Hamiltonian, state system Hamiltonian, and then some coupling. And within this framework, it's a lot easier to determine what is the cost of work extraction. So, and one platform that's quite adapted that fulfill all these criteria here is actually waveguide QED. So that's what I'm going to present now. So my system is still a qubit, as I presented before. And now my battery is a mode of this 1D waveguide, which is resonant with the qubit. So I will use some input-output formalism to describe the system. So I've got some input field, which is a coherent wave packet, represented by this creation operator beta in, that has some average value, which is square root of n dot, where n dot is some photon rate. So it tells me how many photons per unit of time comes into the waveguide and go to interact with my qubit. And then, so this input field interact with the qubit thanks to the coupling gamma between the qubit and the waveguide. And then that gives me my output field, which is given by this input-output relation here. And the second term corresponds to the radiated field due to the qubit, the interaction with the qubit. Of course, I can come back a bit to the maybe picture, which is more usual for some of you if you're looking more at quantum master equations, and I can trace out all the waveguide part, and then my qubit evolution is given by my unitary evolution term, where h of t is my Hamiltonian of the driven qubit, so the bare Hamiltonian plus the field driving, and this Rabi frequency is determined directly by my coupling to the waveguide and my input photon rate and dot. And this kind of framework can be implemented in superconducting or semiconducting circuits, for instance. Yes, and I forgot the second term, of course, is the spontaneous emission from the qubit into the waveguide. So now, before we look a bit more at thermodynamics, I need to define some quantities. So the qubit is prepared in some state, so it has some energy, E, which is the expectation value of the Hamiltonian of the qubit for the state, and some initial coherence, not necessarily, I mean, I can track them both in time, and this coherence is just the off-diagonal element in the density matrix of the qubit. And then I want to look at the different powers involved in this process. So I have the radiated power, which is come from the qubits. And because the qubit is only coupled to the waveguide, it simply corresponds to minus the energy variation of the qubit. Then I've got the input power coming from my driving, which is simply h bar omega 0 times my input photon rate. And finally, the input power, which is the sum of the two for energy conservation. And finally, I need to define what I mean by work and heat to do thermodynamic. And in that case, we chose a really operational definition of work as the energy carried by the coherent component of the radiated field, which means that we take this output field operator and just treat it like it was and look at what's the coherent part of it. And that tells us what's the work. And then the heat is, of course, what remains, so that we get the first law of thermodynamics. And this is a quite useful definition for work because it's directly reusable to drive another qubit. So this is useful energy. And secondly, this is also measurable by heterodynamic techniques, for instance. And finally, before looking at what's the cost of extracting the work, we want to know a bit more. I need to explain a bit more what's the thermodynamic protocol. So we have the qubit, which is initially prepared in some arbitrary state in the Bloch sphere. So again, characterized by this angle theta and this purity P. And this initial state has some initial coherence S of 0 and some ergotropy. So maximum amount of work I could extract with a unitary. And then the battery also has some initial charge, which I could characterize as the number of photons I have in my input field. And then at time 0, I couple the qubit to the battery. And I can define the extracted work with this expression using, so here, this is the population of the excited state of the qubit at time t that I integrate. And then I tell me how much work I can extract from that. I have extracted from the qubit from this protocol. And finally, I can compare this work I've extracted to the amount of ergotropy I initially had in the qubit to see if I manage to extract all of it or not. And now what I want to understand is what's the impact of, on the one hand, the initial coherence of the qubits on this work extraction, and secondly, on what's the impact of the battery charge. So for that, I'm going to look at 3 different scenarios. The first one is a scenario which is non-autonomous with a constant input rate. So I have a constant laser drive, for instance, and I can just connect and disconnect manually my qubit from my waveguide. And I can leave this qubit connected to the waveguide for a time tau, and then look at what's the optimal time to extract the maximum amount of work. And this is what I'm going to call this W optimal, this maximum amount of work I can extract. So for simplicity, I'm going to do it only for pure states. So what I'm plotting is the amount of work I can extract from this pure state rho 0, which has an amount of coherence initially, which is goes as this sine theta, so theta being the angle on the Bloch sphere. So what I've plotted is this amount of work I'm extracting as a function of this angle theta and as a function of the photon rate. So what you can see in the top right corner is what I call the stimulated regime, because this is like the major example I gave you in the introduction of this part, where I can really do a pi pulse which maximizes the work extraction. I got the maximum yield because I got out all the ergotropy from the qubits. And it obviously requires a large initial battery charge, because what I want basically is a classical drive, which means that it costs a lot of photons. So I need a large battery charge to get just one more photon. And there is another quite interesting regime that we can see in that plot is at the bottom part. Around theta equal pi over 2, there is a faint red shade here in the plot, showing that even when I have 0 photon in my battery, or almost 0, I can still extract some work here. And that's what I'm going to explore a bit more in the second scenario. So in the spontaneous regime, I have absolutely no photon initially in the battery. It's completely empty. But I still couple it to my qubit, which is prepared in some initial state. And as we've seen in the plot, we can still extract a little bit of work. And that's because with our definition of work, we can see that a fraction of the spontaneous emission is actually a coherent field. And therefore, we can theoretically use it to, for instance, we could try to drive another qubit. So a non-driven system here can produce work, and we are solely using the quantum coherence here to do that. And this is clearly a complementary resource for work extraction compared to the battery charge. So we are compensating for the lack of photon in the battery initially by the coherence in the qubits. And now I want to look at a bit in between scenario. So I have some initial but finite charge in my battery, n bar, and I have some initial state of my qubit with some coherence. And now I want a scenario where I'm not manually connecting and disconnecting the qubits, like in the first scenario. I'm just sending a pulse with some fixed duration, tau, that I've chosen here to be 1 over gamma. So gamma is this spontaneous emission rate of the qubits. And again, my qubit is in a pure state. And what I get now is this. So the white areas is when the work gets negative. So I'm not extracting work, I'm giving work to the qubit. And the colored area shows where I can extract work. And the first thing we see is that we have this spontaneous regime. So when there are no initial photon in the battery, basically there is no pulse, so it's the same as scenario 2. And here I'm showing the yield. So this is the work extracted, and the work extracted divided by the ergotropy on the right-hand side. If we go to high photon numbers now, we get back to the stimulated regime I presented before, except that now it happens only when the duration of the pulse coincides with a pi pulse. So it's not for any photon number. It only at certain photon numbers. That's why I have these small red areas here. And finally, the quite interesting regime here is that I get the maximum work extraction somewhere in between. And you see that I still have some quite high yield in that place. So let's look at it a bit closer, get a closer look. So if I just plot a slice of these plots here for a really low photon number in the battery, then I get my spontaneous regime, where I can clearly see that the coherence is my resource. And I also see that the maximum yield in that case would happen when I have theta equals 0, so where I'm not extracting any work. But I still have a yield of around 1/2 when I'm extracting the most work. So that's the spontaneous regime. Then I have the stimulated regime here at higher photon number, with a maximum which is around pi, because I'm doing a pi pulse from the excited state. And I don't have such a great yield here because I have quite a small photon number in the battery, 22. So I'm not doing exactly a nice classical pi pulse. But here what I'm exploiting is purely the battery's charge. And now in the middle, what I have is something in between. So I extract more work. I have a good, almost the maximum efficiency coincides, the maximum yield, sorry, coincides with my maximum work extraction. And what's happening here is that I'm using both the charge of the battery, so the number of photons, and the coherence in the qubits to extract more work in the end. So to summarize, I've used here an operational definition of work based on the battery's observable, in that case of a qubit coupled to a 1D waveguide, and the work is the coherent fraction of the field radiated by the qubit. And this is quite useful because it can be directly used to perform unitary operations on another qubit, and it's directly measurable by heterodyning. And what I hope I've showed you in the last few slides is that the qubit's coherence and the battery's charge are complementary resources for work extraction. And if you want more details, they are all in this first reference. And if you're interested about possible experimental application or implementations, there is a related experiment that has been published in 2023. So maybe here could be a place to take one or two questions if they are on this specific part, because I'm going to change topic afterwards.
So time for questions, if anybody has some. I do, honestly. So I let.
Yes, may I ask one question?
Sure, go ahead, Armin.
Yeah, thank you. My name is Armin Alavercan. So thank you for your talk. Now, can you explain a little bit in details? So you said work is something which is not accompanied by entropy, but it was not very clear from your definition where the specific condition comes that you prohibit the increase of entropy. Can you comment on this?
Oh, the specific definition I'm using goes with that, or like
where do we see that you prohibit entropy together with energy, so that it becomes work? Where this entropic aspect is coming in?
Right. Okay. Yeah, it's true. When I give this definition, I'm not explicitly showing that I'm not changing the entropy of the.
So there might be a lot of entropies going around, right? So there might be some coupling between work and heat, right?
If I understood correctly, you are using
heat is energy which is okay with entropy, namely it goes together with entropy, while work is that part of energy which is kind of pure. It goes without entropy.
Yes.
Right?
Yeah.
So if you apply those definitions you presented, then maybe you are doing work together with heat. Is this possible?
I agree with Armin. The dissipator.
Yeah.
But
so
in
that the
principle,
heat
you're
production,
using a
entropy
unitary.
production with the dissipator.
Yeah. I mean this.
The charging process, in principle, is a unitary.
So not the. No, it's. I mean, I'm not looking at a unitary process here, because I have this coupling to the waveguide, which is basically an environment. So there is dissipation here. So it's not a unitary. No, so I would have to check again. Yeah, this is not. Yeah, I should have refreshed more on this. Yeah.
Thank you.
Can I ask a question? Yeah, thank you. Nice talk. Well, this is only one half of it. I'm looking forward to the next half. But I'm just wondering, in the experiments, there's cost for all the preparation of the states and all the measurements.
Of course, yes.
Yeah, can they estimate that experimentally, or can you theoretically estimate the cost of that?
Oh, I mean, this is gonna by far exceed anything you can extract from. So I've not worked on the experimental implementation part. Like I was mentioning it because I know the article exists and like people from this paper also worked on that, but I wasn't involved at all, so I wouldn't be able to. I wouldn't be able to tell you what's the cost or anything
Yeah,
because
I have to look at the paper. Yeah, probably.
yeah.
Hopefully they have some estimate of that.
Yeah,
But in principle,
but
you can, of course, use unitary operations to prepare the state, but even that's
yeah,
not obvious that you can, if you start with a random state, right? You may have to make some, you have to maybe do some measurements in addition to gates if you do
yeah.
quantum circuit. So that costs energy and work.
Yes. Here I'm assuming that I know exactly that the initial state of my qubit comes like for free in the sense that that's not what I'm interested in, quantifying how to get this initial state. I'm assuming somehow I have it and I know what it is. Though, I mean, technically, knowing what it is not that important in the sense that I'm not adapting really the protocol to what I know about the qubit state, but I have not evaluated what's the cost of producing it.
Yeah, thanks.
Oh, yeah, just to come back on the entropy question, I know that Patrick Potts is working on this definition of work and heat to check if they work with the second one something. So I think you have to redefine a bit entropy, but then it works. My last discussion with him was something along these lines, but you would have to ask him, I think.
Okay. Patrick Potts?
Yes.
Yeah, okay. Thank you very much.
Any other pressing question?
If I can ask a quick question.
Yeah.
In your definition of work, does it allow you to estimate also, I don't know if the probability distribution or at least like the fluctuations of work?
So we have not really pushed it beyond average values in that case.
Okay.
But I'm sure it would be interesting to see how much we can push it. So, but we didn't. Yes.
Just maybe for me just maybe to clarify, when you define work in terms of the coherences in the qubit, is that really the definition, or is that a formula that is the result of some calculations? Because let's say what I'm used to is that you can define work as the energy coming from some work source, so like a laser.
Mm-hmm.
And then in the case of a laser coupled to a two-level system, you can carry out the calculation and get some expression like this. So I'm wondering if that's what you did, or if that's really how you defined it from the start.
So I really defined it as the coherent part of the radiated field. So basically I'm taking my output operator and I'm taking the expectation value as if it was a purely coherent field, and that gives me the coherent component. Okay. And then I have something that remains, and that's the heat.
Okay.
That's my definition.
Okay, fine, thanks.
Yeah.
I think it coincides with what you would get from starting from a less ambiguous definition and then just calculating, and then you end up to this.
Okay.
Okay, I have to think of it. Thanks.
Right. Okay, so if there are no other questions, then I'll move on to my second part. So I'm going to really change the setup I'm looking at, and I want to look now at information erasure, so different kind of task, and in a much more classical setup, let's say, in the sense that I'm going to look at classical information erasure. And this is a more recent work in collaboration with Janet Anders groups, so both in Exeter and Potsdam, and with Natalia Ares' group in Oxford. And so the main two really main authors of this work are Joe Dunlop, who is a PhD student in Exeter, and Federico Cerizola, a postdoc in Exeter as well. So I'm going to start from Landauer's bound and see a bit how we can go a bit beyond that and find a tighter bound on this erasure course due to other factors. And so as you probably know, information erasure, so it's also task, which could be quite useful, for instance, in computing, but not only. And this has a cost. And we know, for instance, of Landauer's bound, that tells us that the work cost to erase one bit of information is kBt log 2. But of course, this depends a bit of the situation we are looking at. So in the case of Landauer's, because we have kBt, then obviously we have a heat bath. And I'm going to take a more concrete example of a quantum dot coupled to a single thermal bath, because later on I'm going to look at the case of a quantum dot. So I have a single level quantum dot. So this is this energy level here that's coupled to a single thermal bath, which is just represented here in the energy. So you can imagine the y-axis here is the energy, and I have a Fermi distribution of electrons in this bath characterized by some temperature Ts and some chemical potential μs. So now what is the information in this? So what I'm gonna say is the information is whether the dot, so this level here, is occupied or not by an electron. So it can be 1 electron or 0 electron in the dot. And on average, I have some average occupation, P, which in this simple case is gonna be simply the Fermi occupation at the chemical potential mu of the dot. Okay. So now I have this dot, which is exactly where the occupation is 1/2, and I want to erase this information and be sure that I'm in the 0 state. What I can do is now to bring this, the level of the dot so far up that I'm sure it's empty. That's the first step in this information erasure. But then I want to get back to my initial chemical potential of the dot, so I have to bring it quickly back down, or by decoupling it completely from the bath in some way, so that I get back to the previous chemical potential, but I still have 0 occupation in the dot. So that's my information erasure. And that, of course, is costing me some work to do that, because I'm raising this level with some population here. So the total work cost would be the cost of the first step plus the cost of the second step. In the first step, I have some occupation, P of mu of the dot, during the increase here of the chemical potential. So this is my work cost with the change of chemical potential of the dot here. And the second step actually is free in that case, because my dot is empty. So I can move the level however I want. There is no work involved. So of course, if I do it infinitely slow, this first step, then my population of the dot is just the Fermi function. And then I get back this kBt log 2 bound from Landauer. And of course, if I go faster, there is some irreversibility. My population is not exactly equilibrated, and then it costs me more work. So that's how, for instance, you can get the Landauer bound for this quantum dot coupled to a single bath. Now, this is not always the most relevant bound for practical cases. So if we look at current CMOS transistors, for instance, the switching energy is around 300 times. For the best ones is around 300 times kBt log 2. And in many other cases, actually, it doesn't really fit in this Landauer erasure picture, because there are additional limitations beyond temperature. Maybe we want to do the erasure in finite time. Maybe the reservoirs cannot be considered as infinite nice Fermi functions. There can be strong coupling with the reservoir and many other factors. So here I want to focus on 2 aspects. First, the device geometry, if we want. That is that we can have multiple terminals. So I will look at the case of 2 terminals. And secondly, that there are some form of quantum effects, not coherences and entanglement like in the previous section, but more linked to the coupling to the reservoir, leading to lifetime broadening in particular. So what I want to look at in this part is how we can get a tighter bound than Landauer for a quantum dot. So here that would be the system where I encode my information, which is coupled to 2 terminals. And that accounts not only for temperature, but also for the voltage bias between the terminals and the lifetime broadening of my dot. And for that, we have to go a bit beyond Landauer. So let me first tell you a bit more about the setup. So we have this single level quantum dot, which is at some chemical potential mu, which can be controlled by gates. And I will always call P mu the population, the average occupation of this quantum dot. Then there are two terminals, like I said, that are again distributed by Fermi, characterized by Fermi distributions at respective temperature Ts and Td, so for source and drain. And then they also have their own chemical potentials, μs and μd. And then the coupling between the quantum dot and each of the terminal is given by this tunnel rate, gamma s and gamma d. And I'm going to call gamma dot the sum of the two. So in this problem, we have three energy scales. We have the terminal temperatures. So this kBt energy scale from Landauer. We have the chemical potential bias between the two terminals, delta mu, and we have the lifetime broadening of the dot, which depends a bit on the model we want to use to describe it, but is typically going to be of the order of h bar gamma dot. And now the question is, how do these three energy scales contribute to the information erasure cost? What role do they play in this information erasure? And before I can tell you that, I need to define a bit more precisely what I will look at in terms of erasure cost. So the work received by the dot during the erasure is still given by this formula, but there are different ways of erasing the dot. So I told you about erasing to zero, which would be this case here, where I take my level and bring it as high as I can to be sure it's emptied, and then bring it back really fast. But I could also want to erase to 1. So now I can bring my dot level really far below the bias window and then bring it up again. And because my setup is not, I've not assumed any kind of symmetry or anything in terms of tunnel rates and so on. So there is no reason that these two costs are equal. So I'm going to look at the average work cost, assuming that I need as often to reset to 0 or reset to 1. And now the question is, what's the minimum of doing this operation? So let's look separately at the three energy scales. First, if we are in the regime where temperature dominates, then I have basically the same case as Landauer, except that now I have two different terminals with two different temperatures. So now my population, my dot occupation is a sum of these two Fermi functions with different weights that depends on the strength of the tunnel coupling between each terminal and the dot. And in the end, what we get is a Landauer-like bound with just two temperatures, again, weighted by just the relative strength of the tunnel coupling, of the coupling between the bath and the dot. So that's for the temperature. But now what happens if instead I'm in a regime where the bias is the largest? Then, of course, you can see that now I have to bring my level high enough to be above the source chemical potential. And up to there, I'm going to pay some work to lift my level because my level is going to be occupied. So what we expect is, of course, to see the chemical potential bias delta mu to appear in the work cost. And the occupation now is a much simpler because I can neglect completely the temperature of the leads of the terminals, and I can neglect the lifetime broadening. And so I get just this step function for the occupation of the dot. And if I do the integral and I can compute the work, and I get this different bound, which is, as I said, proportional to the chemical potential bias and the minimum of the two relative rates. So that's the cost of the potential bias. And finally, if now I'm in the regime where the broadening dominates, then now I have to decide on a model to explain, to see how the quantum dot level is broadened. So to say quite general, let's say I have some broadening function G, and then just I do the convolution with the unbroadened occupation of the dot P0. And because I'm neglecting temperature or chemical potential bias here, then my unbroadened distribution is just a step function. And what we can show is that now the erasure cost is directly related to the mean absolute deviation of my broadening function. And you can kind of see it from this cartoon, because now I have to lift my level enough so that my broadening, there is no overlap basically with my terminals distribution, electron distribution. So I have to lift it higher than this h bar gamma dot, which is related directly to the mean absolute deviation of this broadening function. So for instance, if I have a Gaussian broadening, then this d of g is just h bar gamma dot with a square root of 2 pi here, but this is directly related to this total tunnel rate. Okay, so actually the more general function, so we've seen for the 3 different cases in 3 different regimes what happens. But now the question is what happens in the general case, when I cannot say which of the 3 energy scales is dominating. So I've got my 3 bands from before, and what we can show is that actually I can lower bound my work cost by the maximum of the 3 bands. But again, it's not a guarantee that the work cost could be a lot larger. The minimum work cost could still be a lot larger. But the interesting thing is we can also upper bound. So if my actual bounds, W min, which would be if I do the integral exactly for the quasi-static process, the reversible process, then I can show that this is always smaller than the sum of the 3 bounds that I calculated before. So this guarantees me that this minimum work cost is always of the same order of magnitude, basically, as my highest cost in these 3 bounds. So that's quite interesting, because even when I don't know what is the dominating energy scales, when there are several ones that are quite close to each other, I can still use the computation from individual energy scales to get a good estimate of what my minimum work cost. And this can be plotted as well. So here, this is the z-axis is the work cost. And then on this axis, I have the bias, and this one, the broadening with respect, in both cases, to temperature, which is equal in the 2 reservoirs for simplicity. So here I've got the standard Landauer bounds. And when I go toward this side, I see that I get closer and closer to this broadening energy scale. And if I go to the other side, I get closer and closer to the bias energy scale. Right. So in summary, we've derived a tighter bound that really accounts for 3 energy scales that are relevant to this specific setup. And not only did we lower bound the work, but we could also show that this is a relevant bound in terms of order of magnitude. And it clearly shows how the 3 different energy scales play a role in this work cost of information erasure. And as a perspective, we think it would be useful to identify thermodynamic bottlenecks to see how what is costing the most in terms of information erasure in some specific setup, not just the case where temperature is quite irrelevant. For instance, if we are operating at really low temperature, for instance, KBT is probably not being a big limitation here. And second, we would like to apply that to more devices and processes, like, for instance, switching processes. So if you want like the derivation and so on, you can look at it there, all the details in the preprints. And with that, I thank you for your attention, and I just put a summary of the 2 different parts. And I can take question on the second part as well.
All right, thanks a lot, Juliette. Time for questions and discussion. If anybody wants to start. Or I can ask you. So maybe I misunderstood something, but this to me looks like a non-equilibrium system.
Yes.
So what is the temperature that defines the Landauer bound somehow?
So in that case,
Average.
You have some kind of average weighted by the couplings to the bath, yeah.
And this is a tight bound. Fine.
So if you have only temperature, in that regime, yes. If you can neglect the bias and the broadening, then yes, because you just do the quasi-static protocol and then you get the bond exactly.
Is this specific to this particular system? Can we generalize to, I don't know, I have a qubit which is coupled to two environments with different temperatures.
Mm-hmm.
Is it the case?
Yeah. I mean, for this part of the case, yeah.
Okay, interesting. And so something else I'd like to ask is if you, what is your perspective on quantum thermal machines? So what is the main application you think that could be interesting? Maybe from a technological point of view, if you do have a perspective on this.
I
Also
mean,
also in the context of the QEI initiative, no? So we're trying, this is not
of course.
strictly thermodynamic community, this is
Yeah. So, I mean, I think, so first of all, we need to understand, if we want to optimize from the energetic perspective some process, there are some aspects that we need to understand how it works and then to derive the meaningful quantifiers to then be able to do some optimization. That could be a contribution. And otherwise, in more like practical, in terms of technologies, I guess direct on-site cooling directly on chip or this kind of, yeah.
So I agree.
And
for example,
so for instance, I mean, this I've said, like, this is a suggestion. I mean, I don't know how practical it is, how they can, it's probably far from being already possible to put it directly in use, but this one, this absorption refrigerator, they want to use it to reset qubits in quantum computers to some extent.
Exactly, this is what I have in mind, and this for me it's related to Landauer principle somehow.
Also.
Landauer principle, sure, we're talking about erasing information, but most of the times we're talking about purifying a qubit.
Yeah.
In the quantum case. And
yes.
So, of course, like it's more fundamental, it's more interesting for some community to talk about erasing information because it's an interesting connection between thermodynamics, physics, and information. But like in this case, we want to refrigerate quantum systems, and maybe it can be an application for, I don't know, say quantum computing or error correcting. So somehow refrigerating, like freezing qubits is kind of like purifying.
Yes.
All right. So if there is no more questions,
I have maybe a small one, which is maybe a bit related to the question you just asked. So in the second part, so you have these three terms that bound the cost of erasure. So the thermal part is the one we're used to, and then okay, maybe it's a two-part. Okay, I'm not sure I got the difference between the other two. Like so the bias is really the chemical.
Yeah, it's really just the bias.
Chemical potential, and the second one is what?
So it's the mean absolute. Okay, so the broadening is that when I model such a quantum dot in the strong coupling regime, so when the general rates are larger, then I cannot just model it like for Landauer, like just a delta, like an energy level exactly at mu. There is some distribution.
Okay.
And then there are different models to exactly, it's going to, I guess, depend a bit on the exact regime and so on. And one way to generalize that, you say, okay, I have this broadening function, G. So it can be, for instance, a Gaussian function. And then from that, I can see that my cost of erasure, basically it's linked to bringing this broaden level outside of my bias window. So far high enough to empty it. And because of that, I have to displace it by more than this broadening somehow. So it's costing me this broadening energy.
So this broadening is due to quantum effects more than, or
So
maybe
strong coupling to the
strong
leads.
coupling. Okay.
Yeah, it's strong coupling to the leads.
Okay, so then, because then my main question was to ask you which of these terms actually dominate, for instance, in the devices that you use. You have
It's gonna depend a lot. I have in mind a device where typically it's this broadening dominating. So let's say if you put one of these quantum dot chips, for instance, in a dilution fridge, you're typically gonna be in this lifetime broadening regime. If you're but I mean, of course, you could increase the bias until the bias is dominating, or so it really depends on the specific setup.
Okay, thanks.
All right. So thanks, Juliette, for your talk. Thanks, everyone, for the questions, the discussion. So we will announce soon the next seminar for next month. So stay tuned. We will send you the newsletter of QEI. I guess most people that are here already are in the community and receive the newsletter, but pass it to your colleagues and friends. Nothing else. Thanks, everyone.